In this lecture, we'll take a look at the basic chemical consistency of water, its impact on the Earth's many geological systems, and its work as a major player in patterns of weathering as we see landscapes develop over time. You will want to revisit this image, this second slide in our lecture presentation today. It will provide you with a number of important terms associated with patterns of weathering as they relate to, in this case, the actions of water. It will also give you a pretty good understanding of how water, in terms of landscape change over time, will move itself, water particles, and it will carry physical matter from areas of very high energy output to areas of very low energy output. So we can look at even the action of water in a landscape or a landform system through a systematic lens. Both physical geographers and geomorphologists will utilize a great deal of terminology that we see depicted in this image. They will engage the idea of soil processes and soil content. They will take a look at differential patterns of weathering associated with a source area. They will look at the size of particles and even the chemical compounds that are being, in a sense, transported from one section of a landscape to another. And they will connect not only the evolution of a landscape, but the work of water and the movement of particles within that landscape to, in this case, the overall deposit of materials within a watershed system. So as you can imagine, we will be returning to not only this image, but the content of this image in subsequent lectures. Let's talk a little bit about the nature of water as a major element within many earthly geosystems. Water is an important compound in all geosystems. The Earth's hydrosphere contains approximately 1.36 million cubic kilometers of water. That's approximately 326 million cubic miles of water. It is currently believed that the Earth's water originated from icy comets that formed part of the planetesimals that composed the initial Earth body. Planetesimals, and again, not just these icy comets, but any building blocks of planets, are defined as, again, building blocks of a planet. They are part of what is now known as the planetesimal hypothesis, which proposes that early protoplanetary bodies formed from the condensing masses of a nebular cloud of dust, gas, and these icy comets, and a formation process that we see now in other parts of the galaxy was also something that was part of the Earth's initial history. Given this planetesimal hypothesis, it is also believed that the water within the developed planet, in this case the Earth, reached the surface by a process known as outgassing. Outgassing is a continuous process by which water and water vapor emerge from layers deep within the crust of the planet, in this case at least 15.5 miles below the Earth's modern surfaces. This means that in the early atmosphere of the planet, massive quantities of outgassed water vapor condensed and then fell to the Earth as torrential rains. For water to remain on the Earth's surface as it is today, land temperatures had to drop below the boiling point of, in this case, 212 degrees Fahrenheit. Something that is believed to have occurred in this case approximately 3.8 billion years ago. Well, no matter what the actual answer is to the process of how water became part of our unique Earth systems, one of the things that we can agree on is that outgassing as a natural process occurs today. We see it in volcanic eruptions, we see it in the work of geysers and seepages associated with the shallow depths of the Earth's surface. Let's take a closer look at what is referred to as the worldwide equilibrium of water. Really what we're looking at here is the nature of water. Water today is recognized to be the most common compound on the surface of the planet. Its present volume, this 1.36 billion cubic kilometers of material was believed to have been reached as a volume somewhere in the last 2 billion years. Water is continuously being lost from the Earth's natural systems. No matter how old we believe the current volumes of water on the surface of the planet and even just below the surface of the planet are, in terms of when we reached those volumes, we do understand something about how water behaves in our modern landscapes. Water is lost, as I said, when it disassociates into its basic chemical components, in this case hydrogen and oxygen. Water is also lost through the atmosphere, being expelled into space along with the heat energy from the surface of the planet. Pristine water resources, not previously at the Earth's surface, replace lost water resources when it is expelled from our crust and from our atmosphere, meaning that though a stable balance or an equilibrium is always reached within the Earth's hydrosphere, changes and fluctuations in the Earth's water resources occurs. These are eustatic changes, and when glaciers are involved, so glacial to oceanic water transfer is referred to as a kind of glaciostatic process. So what's the moral of the story here? Well, like every other natural system on the planet, systems that involve water itself becomes a very, I don't want to say random component to how they behave, but it is a component that is dynamic. For example, some 18,000 years ago during the most recent ice age and fluctuations in global temperatures that were part of that ice age period, sea level was more than 330 feet lower than it is today. More water was being stored in glaciers worldwide than what we had in terms of many of the surface flows of our continents. It reduced, in a sense, the overall sea levels. Water was being gathered up into these glacial bodies. 40,000 years ago, before this period, sea levels were at a level 500 feet lower than they are today. So what does this tell us? It tells us that many of the landscapes associated with our marine environments have gone through several very extensive changes as it relates to their relationship with water. And those changes are also very much a part of the history of glaciation as it relates to the planet and its change in global climate. We continue to see change with regard to the effects of climate on water and its work in a variety of other systems, really over the last century. Today, when we take a look at mean sea levels, we realize that they have risen as much as 16 inches over the last century to a century and a half, and they are still rising today. We attribute these rises to a warming trend in our global climates. Whether this rise in global temperature and subsequently this rise in mean sea level is the result of a long-term natural process, or if it is part of our contributions with regard to the industrial age, or some blending of the two, doesn't necessarily matter at this point. What matters is that when we look at water as it behaves, and as if we look at global patterns of water volumes through a systematic lens, we realize that it is dynamic. It's in a constant change of feedback and flux, and it is closely tied to a variety of other historical natural qualities that the Earth has regarding itself and how it continues to evolve over time. To understand how this connection plays out, or how water functions in the landscape, we have to understand something about the heat properties of water. As is the case with the Earth's many systems as a whole, heat energy represents a systematic output, and the work of the sun, and that includes heat as well, acts as a systematic input. So, as is also the case with a number of other earthly systems, we know that water will leave the Earth. It will be a kind of systematic output. It joins the electromagnetic energy or infrared energy terms of a portion of that spectrum, in this open state quality that we now associate with the Earth and its natural systems. We also know that water likes to, in a sense, or is susceptible to, being changed from one state to another. It depends on the circumstances of where the water is and what's occurring around it. So we know that water occurs in a solid state, a liquid state, and a gaseous state. When water is manifesting itself in each of these three states, we know that the heat energy is either being absorbed or it's being liberated. The heat energy that is, in a sense, part of whatever volume of water we're looking at as transitioning at any particular time in a seasonal cycle, in a weather cycle, or in a long-term climactic cycle. This relationship between water and heat is very important in terms of how we connect the chemistry that we associate with water with all of the other earthly systems that surround it. And one of the strongest connections that we see is with atmospheric processes. The heat exchanged between physical states of water provides more than 30% of the energy that is required by the atmosphere to power its circulatory systems, or in this case, the general circulation of the atmosphere itself. This makes the heat properties of water, how it behaves as it moves from one state to the next in terms of its overall expression at any given moment, a major factor in the energy that's required by the atmosphere to function. So, when you're talking about life on the planet, and you're talking about the role of the atmosphere, how water behaves within that atmospheric environment is integral to maintaining the ability for life to exist on this planet. Well, let's step back and use a kind of a larger scale now to look at water and how it connects to local landscapes, and we'll look at it through the lens of groundwater. Groundwater is an important component in our study of things like weathering, how soils form and develop over time, and of course how the planet is able to support life in terms of nutrients and minerals that are ultimately stored within local soils. Groundwater is probably one of the most important elements within the hydrologic cycle. Today, physical geographers recognize groundwater to be that portion of the hydrosphere which lies beneath modern surfaces, extending well beyond the soil moisture root zone in local soils. So in a sense, groundwater does not exist independently of surface water resources. Surpluses in water resources at the surface replenish the water volume below those surfaces. Excess surface water moves through the pores of soils and rock debitage within the zone of aeration, a physical location below the ground, deeper levels in this case, where we see a greater degree of soil porosity, where we see more aerated soil. And then soil moves beyond that into a zone of saturation, where it fills those open pores and in a sense is stored there to be utilized by other organisms at a later date, or to move into, in this case, the zone of aeration when water deficits are occurring in local landscapes. At this point, it's important that we keep in the back of our minds the notion that the location of the groundwater, or the groundwater table, is different from the measure of water that we associate with our study of soils, in this case the soil water budget concept. Groundwater as a resource is really part of gravitational water, water that is translocating through modern soil horizons, eventually interacting with the groundwater table. The physical zone that we associate with the groundwater resource then within the lithosphere generally overlaps with what I mentioned before, which is this zone of saturation. So where do we find groundwater in terms of this natural resource? Well, wherever we can measure or identify the location of a local zone of saturation. That zone of saturation then would represent a physical location in the landscape where water is in existence year-round. It inhabits the pores between rock debitage and soil particles year-round. So as you can imagine, the size of our groundwater resources as they relate to the entire lithosphere makes groundwater very, very important. Really, it's the largest potential source of fresh water within the Earth's hydrologic cycle. Its capacity is larger than that of all of the Earth's surface lakes and streams. Between the level of the Earth's modern surfaces and an arbitrary depth of approximately 4 kilometers worldwide, there exists over 2 million cubic miles of groundwater by volume. This means that the volume of groundwater globally represents an amount of water that is 70 times all of the freshwater lakes and their contents in the world combined. Despite its volume, however, it is a natural resource that needs constant supervision and management, and it needs to be continually replenished. As you can imagine, the chief threat to groundwater and its usability is surface pollution. So in terms of the moral of the story, one of the things that we have to keep in mind is that groundwater, though it is something that we are treating conceptually different from all other parts of the hydrosphere, is not an independent source of water by itself. It is tied to surface supplies and is the principal source for recharging those surface water flows. Additionally, water, in this case groundwater, is very much a part of local human ecosystems. The United States has a dependency on groundwater for its freshwater resources. This dependency continues to increase as populations continue to rise, and in terms of our use and need for water, as that also continues to rise. Between 1950 and 1995, for example, annual groundwater withdrawal increased by 150%. In states such as Nebraska, for example, groundwater resources supply over 85% of the water needs of the state and its occupants. Within Canada, a major resource for productive aquifers, we'll define what these are in just a moment, the rural populations utilize over 53 billion cubic feet of water resources every year. So the strain on this portion of the hydrosphere is significant. Now let's look at some of the basic concepts that we associate with water resources and the groundwater table. First, let's look at what an aquifer is. In this case, an aquifer is a rock layer within a landscape that is permeable to groundwater flow. There are different kinds of aquifers. A productive aquifer is something that is associated with the ability to yield fresh water at depths just below modern surface levels. So it's a very shallow expression of an aquifer. As you can imagine, productive aquifers are highly susceptible to contamination due to their shallow depths. Take a look for a moment at this map image that contains both Canada and the continental United States. Take a look at where productive aquifers are commonly found. In this case, you will find that productive aquifers are very common to, in this case, western and western central portions of what is today Canada and the southern border of the Hudson Bay region. Watercourses are productive aquifers that are adjacent to perennial streams. Perennial in this case refers to water resources that are constantly available no matter what time of year it is. Common watercourses that we would study more closely as a resource within our understanding of physical geography and within the readings for this course would include major river systems. So you take a look at the Colorado River or the Red River, or you take a look at the Mississippi River. These are watercourses that are very closely connected to, in this case, systems of aquifers. In this case, they represent a kind of productive aquifer that is adjacent to a year-round system of flow. Consolidated rock aquifers are often found at lower levels. They are separated from surrounding strata by aquicludes, or nearly impermeable rock layers. Waters exist among consolidated rock particles, those of similar size and shape, with a similar system of internal organization. These consolidated rock layers also have similarly organized intraclastic spaces, or pores, between clasts. In the American Northwest, these are often found in igneous rock layers. Elsewhere, they are found in sedimentary sandstones and limestones. We see in the American West, for example, in the Great Basin region, quite a bit of igneous deposit, that ancient igneous deposits that in a sense are home to these consolidated deep rock aquifers. And this is good because they ultimately are protecting the water from contamination. We see the same kind of consolidated rock aquifers associated with the eastern seaboard region and the Appalachian region. In places like Kentucky and Tennessee, these deep consolidated rock aquifers that are in a sense surrounded by sedimentary rock that includes even things like limestone, have helped to not only preserve water from contamination, but they have acted as a kind of natural system of cleansing the water, or cleaning it in a sense, almost softening the water. This has attracted a number of industries that require water for production. The last groundwater concept that we will associate with these natural stores of water and water resources are combination aquifers. Combination aquifers may contain a degree of non-lithified sands and gravels that are also organized into stratigraphic layers above and below zones of productive aquifer materials. This, as is the case with our consolidated rock aquifers, acts as a kind of filtration system that helps to maintain water resources and their purity for consumption. These kinds of combination aquifers are very common to the American West and the Four Corners region of the American Southwest. Now let's take a look at the role that groundwater plays in the process of weathering. And as I said earlier, we will in a sense return to the topic of weathering several times as we begin to look closely at how landscapes will initially develop and then change over time. When we're talking about groundwater and the weathering process, one of the more important processes within this that we look more closely at is the concept of the mass movement of earthly particles. Here we see the action of groundwater best expressed in terms of weathering. It involves the degeneration and movement of specific landscape materials, and sometimes these materials are reduced to chemicals in solution and then transported again from areas of high energy to low energy. One of the best known landscapes, and it's below ground that we find this kind of landscape, to be associated with groundwater and the weathering process is a karst topography, or a karst landscape. Limestone, or the building block of a karst topographic environment, is abundant on the earth. Local limestone landscapes are susceptible also to things like chemical weathering. Such weathering creates a specific landscape of pitted, bumpy surfaces with poor surface drainage and well-developed below-ground water channels. These landscapes are known as karst. Now, we recognize four basic characteristics to be associated with a karst topography. Let me list these out for you. First, the limestone, that's such an important part of a karst landscape, is in a sense going to form the regolith of parent resources throughout that landscape. So the landscape itself must contain at least 80% or more of a calcium carbonate based sedimentary rock. Well, limestone and anything within the limestone family will accomplish this first task. Second, there must be complex patterns of rock joints to allow groundwater the opportunity to form, in this case, routes of subsurface drainage and potentially subsurface areas of weakness. Third, we must have an aerated or air containing strata that's below ground, or at least below the ground surface. And we hope that it is also below the local groundwater table, further ensuring water intrusion and, in this case, chemical weathering. And then fourth and finally, in a karst topography, vegetation must be present at the surface. Vegetation in a karst landscape represents an important source of organic acids that enhance and accelerate the weathering process. So if you have visited systems of caves or cave systems within the Midwest, at least the upper and central Midwest, or if you have traveled to the American South or Southeast and visited some of these large subterranean caves, you're walking through a landscape that in a sense is created by weathering, specifically weathering associated with groundwater. In these same environments at surface levels, we see the development of sinkholes. Sinkholes are circular surface depressions that result from below ground collapses of, in this case, limestone layers or any sort of sedimentary rock that is susceptible to the weathering that we assign to groundwater and the movement of water particles through that groundwater table. A second kind of landscape that is very strongly associated with the work of water particles in this case, below ground surfaces, or the movement of chemical compounds and materials through local landscapes, is or are landscapes that are associated with things like soil creep and surface slump. In both instances, we have a systematic imbalance that is associated with an increase in the volume of soil water, and eventually a soil water volume that makes its way to that zone of saturation. Basically what's happening is we have a landscape that is becoming saturated with water. Here the weathering process connects to the actual movement of huge sections of local landscapes. It is, in a sense, a landscape's attempt to reestablish some sort of stable equilibrium, even though we know that those stable equilibriums are momentary in terms of nature. This example of a pretty massive expression of landform change as it relates to soil moisture levels and the work of groundwater we find in Jackson, Wyoming. This is an example of creep. Creep is the persistent, gradual mass movement of surface soil on a pretty large scale. Individual soil particles are lifted and disturbed by the expansion of soil moisture from below the surface. In a sense, it's almost like you are dealing with small water wheels as that water begins to exist in different states given changes in temperature. We're also seeing another important characteristic, which is you need the presence of water in these soils to be able to create those small, tiny disturbances that literally will move or shift an entire landscape from an area of higher elevation to one of lower elevation. In this case, the cycle of freezing and thawing is an important part of understanding the speed of the process. So soil creep and surface slump represents a second type of landscape that is directly relatable to the weathering practices that we associate with groundwater. The other was the karst topography.